In this lecture, we'll continue our discussion of semidirect products. So I want to start by just recalling some of the things that we proved last time. So we showed that if H and K are groups, and phi is a homomorphism from K to the automorphism group of H, then the set of all pairs H comma K, where H is in the group H and K is in the group K, with the multiplication defined in this way, forms a group called the semidirect product of H and K with respect to phi. So what is this multiplication? HK times H prime K prime is H times the automorphism phi K applied to H prime, and then K prime in the second coordinate. So in the last lecture, we talked a lot about where this comes from, how it's inspired by the case where H and K are both subgroups of a common group G, and H is normal in G, so that K acts on H by automorphisms via conjugation. Okay, so now we saw at the very end of the last lecture some examples of semidirect products, and we're going to see a lot more in this lecture. So one that you can always take is there's always one nice way to write down a homomorphism from K to the automorphism group of H, no matter what H and K are, which is just take the trivial homomorphism. So what does that mean? So for each K, little k and K, we get an automorphism of H. Let's always choose the identity automorphism. So phi K of H is H for any K in the group K and any little h in the group H. So with this choice of phi, what does multiplication look like in this semidirect product? Well, HK times H prime K prime is H times phi K of H prime times KK prime, which is H times phi K of H prime is H prime, because phi K is always the identity automorphism of H. So we get H prime in the first coordinate, KK prime in the second coordinate, and this looks exactly like the multiplication in a direct product. Why is that? Because when you choose the trivial homomorphism, this semidirect product is the direct product. So if you just take the identity map of sets, where you take a pair H comma K and you send it to H comma K, the first HK is in the direct product and the second HK is in the semidirect product. This is an isomorphism from H cross K, the direct product, to H semidirect product K. So why is this an isomorphism? Well, it's always a bijection of sets, right? I mean, you always just can take a pair H comma K in this and send it to a pair H comma K in this, and it's definitely a bijection because the underlying sets in these two groups are the same. But usually the multiplication is different. But in this case where you pick the trivial homomorphism, the multiplication is not different. So how do you check it's a homomorphism? Well, that's just like saying that the multiplication on the left side and the multiplication on the right side need to match up. And the multiplication on the right side, we're going to need this H times phi K of H prime, KK prime, to be the same as H prime, KK prime. So this is only a homomorphism when phi K of H prime equals H prime for any K in the group K and H prime in the group H. But what does that actually mean? So if you fix one element, little k, it has to send every H prime to itself. So every fixed phi K has to be the identity map from H to H. But if you send every element K in the group to the identity element of aught H, the identity automorphism on H, that is the definition of what it means for phi to be the trivial homomorphism. Okay, so what are we seeing? We're seeing that the semidirect product with respect to phi is isomorphic to the direct product if and only if phi is the trivial homomorphism. So we'll see some similar things like this. I'll pause and erase, and I'll prove some similar statements and then I'll write them all up together as one proposition. In the last lecture, not only did we see that H semidirect product K was a group, but we studied two particular subgroups, H tilde and K tilde, inside of this group, where H tilde is all the pairs of things that are something in H, comma, the identity of K, and K tilde is all the things of the form identity of H, comma, something in K. We saw that H tilde is isomorphic to H, and K tilde is isomorphic to K. And moreover, we saw that H tilde is always a normal subgroup in the semidirect product, because when you conjugate an element of H tilde by an element of K tilde, you get something back that's still in H tilde. So what does that really mean? That means that K tilde is in the normalizer of H tilde. And why is that enough? Well, I'll come back to that in a second. So let's look at when you conjugate by K, an element in K tilde, and you actually get back the same element in H tilde. Well, just using this formula, this element on the left is H comma 1 if and only if 1K H1, 1K inverse is H1. That means that this phi K applied to H always has to be equal to H for every K in the group K and every H in the group H. But that means that for every K, phi K is the identity automorphism of H. And if that's true, then phi is the trivial homomorphism. OK, so what have we seen? What does it mean for something in K? When you conjugate something in H tilde by something in K tilde, you get back the same element in H tilde. It just means that those two elements commute with each other. Right? If x, y, x inverse equals y, then that means xy equals yx. So what are we seeing? We're seeing that every element in H tilde commutes with every element in K tilde if and only if phi is the trivial homomorphism. OK, so let me now go back to this issue about why this is enough to show that this is a normal subgroup. So we're going to review something we talked about last time. Since every element in the semidirect product can be written as, OK, so it looks like something in H comma something in K, you can write that as a product, something in H tilde times something in K tilde. So what we want to understand is, when is K tilde a normal subgroup in the semidirect product? Well, K tilde is a normal subgroup if and only if H tilde is contained in the normalizer of K tilde. So why is that enough? So you know the normalizer is a subgroup, and K tilde is definitely a subgroup of its own normalizer. So if H tilde is also a subgroup of the normalizer, then everything in H tilde is in the normalizer, everything in K tilde is in the normalizer. So you take the product of something in H tilde and something in K tilde, and you're still in the normalizer. But that's the whole group. So that's what it means for K tilde to be normal. This is the exact same argument that we used up here. So why is it enough to see that K tilde is in the normalizer of H tilde to show that H tilde is normal? Because H tilde is always in its own normalizer, and everything in the whole group can be written as a product of something in H tilde, something in K tilde. OK, so now let's see. What do we have to check? We have to check, is H tilde in the normalizer of K tilde? What happens when we conjugate an element of K tilde by an element of H tilde? So let's just see. H1 times 1K times H1 inverse. Well, H1 times 1K is HK. So, and H1 inverse is H inverse 1. So what we get here is H phi K times phi K H inverse, and then K over here. So when is this in K tilde, right? When do you conjugate an element in K tilde and get some other element in K tilde? Well, exactly when H times phi K H inverse is the identity element of H. But when would that happen? That is only true when H times phi K H inverse is the identity. And that's only true when phi k H inverse is H inverse. So what do we need? We need it to be the case that for every little k, phi k sends every H inverse to itself. So phi k has to be the identity automorphism of H. And if phi k is always the identity automorphism, that means that that phi is the trivial homomorphism. So what are we seeing here? We're seeing that k tilde is also a normal subgroup in the semidirect product if and only if phi is the trivial homomorphism. Another way to say that, we've already seen that phi is the trivial homomorphism if and only if the semidirect product is isomorphic to the direct product via this identity map. So k tilde is a normal subgroup also exactly when the semidirect product is isomorphic to the direct product. Okay, so I'll pause and erase, and I'll write all this up together as one proposition. Let's review what we've shown in this video so far. This is basically proposition 11 in section 5.5 of Dummit and Foote, plus I've added one extra equivalent statement that comes from Conrad's notes on semidirect products. So let's let H and K be groups and let phi be a homomorphism from K to the automorphism group of H. The following are equivalent. So these are going to be 4 statements. Each one is equivalent to every other one. The first is that the identity map of sets between H semidirect product K and H cross K is an isomorphism. So the direct product and the semidirect product are isomorphic to each other by just taking the pair HK and sending it to the pair HK. The second statement is that phi is the trivial homomorphism. The third is that k tilde is a normal subgroup in the semidirect product. And the fourth is that every element of H tilde commutes with every element of k tilde.